same idea, I'm just going to call it zeta. All right, so I can look at some change in the amount of reactant or products in terms of moles as a function of zeta. I can track progress. So here's an example. Here's the generic equation, A plus B going to C plus D, with just some reaction coefficients that have been generic. If I want to put real reaction coefficients, let's just say 2 A's plus 1 B is going to go to 1 C and 2 U's. All right, so here's the reaction trajectory of A, B, and C and D. And what I immediately notice is the slopes aren't all the same. All right, so why are the slopes of B and C different than A and B? So, okay, so right. All right, so first things first, the slopes of A and B are definitely negative, C and D are positive. Definitely right. A and B are being consumed, C and D are being made. All right, how about C versus D? Yeah, so that's where the stoichiometric coefficients come in, right? I'm making 2 D's for every 1 C that I make. All right, so even if I did not have what's in blue, I could probably figure out, right, if I can measure the slopes, which I probably could do with a ruler, and maybe a simple equation, right, I could figure out the stoichiometry of the reaction. All right, so easy enough. So if I think of the chemical potentials and I think of stoichiometry, the stoichiometry is important to me. I can think of things in terms of a seesaw, in terms of being balanced. But basically, when I think of the situation at equilibrium generically, if I have lots of reactants and lots of products, basically everything on the left is going to equal everything on the right at equilibrium. Meaning that whatever my stoichiometry coefficient times the chemical potential of A being consumed with B being consumed is equal to that of the chemical potential of C and D. All right, so in the case before, right, things aren't all scaled 1 to 1 to 1 to 1, but rather 2 to 1 to 1 to 2. All right, so that's going to factor in and how to balance this out. But the situation of equilibrium, just remember all the chemical potentials and the stoichiometric coefficients have to all add out and be equal to each other on the left and right side of the equation. All right, so if I think about this whole thing in terms of reaction progress zeta, this is a typical curve, and then the big thing to remember at my equilibrium point, right? So this is just G as a function of zeta. Remember at my equilibrium point, my global equilibrium point, that derivative is equal to 0. And if I'm going towards equilibrium, it's negative, right? So this is going towards it to the right. If I'm going away from it, my slope is often positive. So basically the same thing that we saw from last class. I'm just now calling things zeta instead of x. All right, but you can think of chemical potentials now. All right, so generically, you all should be able to set up equilibrium constants. That's really important to us. The only thing I'll point out, right, if I'm doing standard conversions into delta G naught, just remember if I have stoichiometric coefficients, the base concentrations by those stoichiometric coefficients. So here's the generic equation, right, and I've just raised everything to a power. I think you all know that. And then of course, this is how I think about setting. All right, so the convenient thing that I can do now is to start thinking of using this KEQ to calculate extensive reactions at equilibrium. And so we said, all right, in this particular case, ADP plus water going to ADP and PI, I have a delta G of about minus 30 kilojoules per mole. All right, so generically, am I on the left hand or the right hand side? Given that delta G. Right. This is the important point. This is the internal check when I do KQs. It's favorable, right? All right, so should it go forward? It should go forward, so it should be at the right. All right, so the critical thing is, okay, well, that's fine, but how much to the right? All right, what is the extent of the reaction? So this is physiologically reasonable. Let's say inorganic phosphates maintained at 10 millimolar. All right, so can we figure out the extent of the reaction? Obviously, the answer is yes. All right, so this is how we would do something. This is how we would do a problem. Sorry. All right, so if I want to set up an equilibrium like that, right, so again, this is just ATP plus water going ADP plus PI. If I want to set up the equilibrium constant, right, as just equal to K equal to ADP times PI all over ATP. All right, so I'm going to say just easily, right, RT, I'm just going to kind of use standard cellular. R is going to be 8.314 as always. T, I'm going to say, is about 300 Kelvin. Room temperature, more or less. If I go through and do this, this is about 2,500 in terms of joules, right? 8.314. I'm just going to put it in terms of kilojoules, so this is about 2.5 kilojoules per mole. That's my simple one. All right, so if I want to set up a K out of this, mathematically, what's my K equal to? Generic equation. All right, what's delta G equal to? Minus RTL and K. We learned it from algebra, right? All right, so I want to isolate K. E to the minus delta G over RT. Absolutely. All right. So that's my K. All right. So that's handy to me. All right. So under standard conditions, I'm not going to tell you anything about. I'm not going to tell you. Let's assume nothing about PI yet. All right. So my K's equal to minus ATP hydrolysis, minus 28, about that. So minus 28 over, that's about 2.5. All right, so if I go through and do this, my K is about, I'm just going to say about 10 to the 5th. How awful is green back there? Really awful. All right, so that's without knowing anything about PI. All right, but now I can say, hey, let's make this assumption that PI is around 10 millimolar in the cell. It's actually pretty accurate. All right, so that's basically right, 10 to the minus 2 molar. All right, so what this means is if I set up that equilibrium, ADP PI over ATP, I now know something about that term. All right, so I'm going to set it up that way. So ADP now times PI, which is going to be, okay, that's 10 to the minus 2 over ATP equals 10 to the 5th. All right, so what's my ADP over ATP ratio? ADP over ATP equals 10 to the 7. All right, so way to the right or way to the left? Oh, sorry. ADP, yeah, ADP over ATP is 10 to the 7. So is most of it to ADP or most to ATP? That was all of it, right? Like 10 million to 1 ADP. All right, so I'm going to give you another example. All right, so here is another example, and maybe take 5 minutes to do it, because maybe that would be useful instead of me to show you. All right, so here is another reaction. Here's glycerol 1-phosphate going to glycerol and inorganic phosphate. I'll tell you what the delta G is. The delta G naught of that reaction is about -9.2 kilojoules. All right, I want you to do the same thing. I want you to figure out the ratio of glycerol 1-phosphate to glycerol. Or opposite. And again, same idea. Phosphate has the inorganic phosphate concentration hasn't changed, just around 10 millimolar in the cell. So basically set this up the same way. Set up K without knowing anything, and then once you have that, integrate in the phosphate concentration, and then you should be able to get the ratio out of that. This is a useful conversion because it's going to tell you basically how to scale delta G to whether you're on the right or left hand side. Obviously the number is going to be different. We only take 5 minutes to do it, and then we'll just go through it. You'll get equilibrium constant. Generically, what is it? Glycerol, phosphate over, I'm just going to G1P. All right, so determine the K out of it. Generically, right, K equal to E to minus delta G over RT. Now, plugging in the numbers for us, E to the what? 9.2 over 2.5. All right, if I want to do this in base 10, which I'm just going to convert to, that's about 10 to the, this is kind of awkward, 10 to the 1.6 power. You can multiply that out if you want. So now I do the situation where I know the inorganic phosphate concentration. So basically that means glycerol over G1P times 10 to the minus 2 is all equal to 10 to the 1.6. All right, so what's glycerol over G1P then? 10 to the 3.6, which is about 45. 45. It's about 44,000. About 45. All right, so definitely to the right still, but not nearly as much as the previous one. 4,500 products, 4,500 in terms of picking up the glycerol versus the G1. All right, so numerically different numbers. Still favorable, it's still going to the right-hand side, but clearly the extent of the reaction is not nearly that of the other one. You can do this for an unfavorable one, the internal check right should lie to the left. So that's kind of useful.
Would that be glycerol over G1P instead of glycerol on P?
Yes. Yeah. I did it the opposite. Yeah. Yep, you're right. All right. So the things to remember is I think you know this, right? Delta G is not delta G naught. Delta G naught is a standard free energy at very specified conditions. Have you guys seen Q before? Yeah, okay. So you know that Q is what's called the reaction quotient. This is basically, so, you know, K defines, it's particularly KQ when I call it, right? That defines some equilibrium values. When I have non-equilibrium values, I often call it Q. The difference is, right, I set them up all the same way, but instead of like some standard concentrations, they're just some observed concentrations. So they deviate from equilibrium conditions. They're non-equilibrium. The beauty of Q, right? I mean, I can relate standard free energy if I know Q, if I know my non-equilibrium, right, to what my delta G is. I know what delta G naught. That's equilibrium concentrations. This is my equilibrium conditions. So what that means is if I combine these two equations, which is pretty easy to do, right, I will get a non-standard delta G equal to plus RT of Q, my non-standard versus my standard constant equilibrium. Okay. All right, so there's a defined relationship of Q and K in order for things to be spontaneous. Because I can think about, all right, well, what do I need, you know, to get that L, to get this full Ln negative? All right, so you know, where should Q be relative to K? Should it be smaller, right? Because then I'm going to take the Ln, and then things are going to be negative, right? RT is always going to be positive, so that's how I'm going to get a negative delta G out of it. All right, so the other kind of beautiful thing about it, to think about it, is that, I mean, we're not dealing with equilibrium conditions in everything in our everyday life, right? We're dealing with non-equilibrium. What this means is where I poise things versus non-equilibrium, right? Where I am with this ratio is gonna determine how much delta G I can get out of it. All right, so ATP is a great example. If I'm coupling reactions to ATP hydrolysis, I can change Q and K. All right, so in the cytoplasm, for example, ATP over ADP concentrations are non-equilibrium, right? They're 1,000 to 1. There's a lot more ATP than ADP. So I can't really just think of ATP hydrolysis, right? That's driving all the way the other way to ADP. So if I go and calculate the delta G that comes out of it, because of this large Q value, I get a different delta G out. So if I think about it at equilibrium, right, we said, okay, yeah, that's minus 30 kilojoules per mole. But if I poise ATP and ADP in this way, I actually get minus 60 kilojoules per mole out. All right, what this means is I can regulate how much delta G I get out of any given molecule by changing the concentrations I'm dealing with. All right, and that's what biochemistry does, right? It achieves non-equilibrium conditions on these things. So I can get more or less energy, I can poise things in various ways. So this is just a table kind of illustrating that point. These are different Q to K ratios. Obviously the Q to K equal to 1, that's equilibrium, which is Q equals K. Right, and that will tell me, so this is a delta G, and it's just kind of showing relative to that. All right, so you can get different energies out, which is the critical thing. The higher ATP to ADP, right, the more I can get out of this. So that's all that says. All right, so what that means is, depending on how much delta G I get out of ATP, I can use it to drive different types of reactions. And we said, okay, in these couple of reactions, that's what I may need. All right, so not surprising, biochemistry is all about equilibria. You know that. What we're going to do, well, what we will do next class is what you should remember is the pKa's of amino acids, right? You can probably learn them all over the place. pKa of a histidine typically is what? You gave us a chart?
Yeah.
All right, so you should know some of them. Histidine's about what? 6.6? All right. What's an aspartate side chain? It's acidic, lower than 6.6. All right, so you should remember that. Now, well, this is the good news. All right, so take all that. That's standard, right? All right, really, really standard. So we can change them. All right, so one thing that I will say, I think I probably said this in a couple lectures ago, histidine, really, really good for triggering switches. Really good switching, really good amino acid for catalyzing different reactions. Why? It's near neutral. So what that means is I can protonate and deprotonate it. Beautiful thing to be able to do. So I can use it as an acid, I can use base, I can use it as a hydrogen bond donor, etc., etc. I can modulate it. All right, so what we're going to see is, yeah, the standard table is awesome, but things vary, right? Things vary in the environment, things vary depending on what's around. All right, so there are amino acids that are better for different types of functions. Sensors, if I want to protonate and deprotonate, something near neutral is good. If I'm always protonated or always deprotonated, there's not much I can modulate, right? All right, but they're still useful, right? All right, so what we want to do is focus how equilibria can be modulated by local environment. All right, table is good, but it's really, really standard. Yeah, I know a tyrosine side chain is about 10, but that's idealized. That's free tyrosine in a bucket of water. It's not on a protein. Same thing with a cystidine around 6.6. That's generic histidine, not within a hydrophobic environment of a protein. So the equilibria are going to matter. We will change pKa's pretty drastically in some cases. All right, so I'm not going to do this. You know what acids and bases are. You know what strong acids are, and conversely, you know what weak acids are. Fine. All right, so also review. Two fundamental equations. I know you've learned Henderson-Hasselbalch about 5,000 times, right? All right, so when I think of deriving, can you all derive Henderson-Hasselbalch? You don't want to? It's a really easy derivation. All right, so if you want to, let's say you want to derive it. All right, we're just thinking of, I use my hand instead of a eraser. All right, that's probably why. All right, so if I want to set up Henderson-Hasselbalch, right? It's just simple, right? H plus over A minus. I know you all know the final equation, right? But that's it. That's my equilibrium. All right. So what's the next step in the derivation? What would you guess? Knowing what the final result is. You all know Henderson, right? pH equals what? Ka plus something. All right. So, well, what's in that equation? There's a log in there, right? All right. So the logical place to go, right, would be, take log base 10. I'll draw it once, and then I'm going to omit base 10. But then equals to some log of H plus log of, let's just say A minus over HA. I'm going to omit brackets because I'm going to be sick of drawing them after a while. All right, so that's pretty good, right? Because log of H plus is just simply minus pH. And then I can rearrange. All right, so the other one, Van Hoff. Ooh, is that harkening back a while? All right, you remember the Van Hoff plot? No? Here, I'll tell you the final result, and then this one will derive really quick. All right, so here's the final plot. ln K over 1 over T. Is that one ringing a bell? From way back? All right. All right, so think about it this way. How am I going to derive it? Derive this relationship of K and temperature. Well, what is it going to look like? Is this a line? Is it a curve? Yeah, biochemistry loves lines. Okay, yeah, it's a line. Cool. All right. So how do I go from K to T? These are all standard. All right. So what's that all equal to? What's delta G equal to? Minus RT ln of something, right? K. All right, so then that becomes easy, right? Because I could just take an ln. So basically where that leaves me is ln of K is equal to minus delta H naught over RT plus delta S naught, and now that my temperatures cancel, over R. All right, so that's the van off. So if I make a plot like this, right, here's the plot. What's my slope equal to? My slope is going to be minus delta H over 1 over T is my X, so just over R. And my y-intercept, here's my B, right? So just generically, X equals 1 over T, right? Y equals ln K. So I can just think of this as mx, so m is minus delta H over R, delta S over R is my B. All right, so that's the generic one. All right, so what we will do on Monday is we're going to talk about pKa. So hold back on, I think it's question number 3. It has a warning on it. If you want to hold till Monday, hold till Monday. Because that's an all pKa modulation type problem. We'll go through a sample, so hold back if you want to. The homework's really quick. If you do not have your exam 1 and you like it, I have your